So let's start with the second class of superalloy, which is cobalt based superalloy. So cobalt based superalloy differs with respect to the other class of superalloy because they don't show the precipitate coherent with the matrix. So cobalt based superalloys don't show precipitates coherent with the matrix. So they are strengthened for the largest part by the presence of carbides, and this is the reason why in cobalt based superalloy we will find a carbon content which is higher than found for iron and nickel based superalloys. So we have presence of carbides which leads to higher percentage of carbon in comparison to iron and nickel based superalloys. Cobalt based superalloy presents a simple microstructure and benefits of the presence of nickel, tungsten, and vanadium in solid solution for strengthening. So it presents a simple microstructure. So we have major alloying element, that is chromium. So major alloying element is chromium. So we use chromium to basically chromium provides oxidation and corrosion resistance. So the content of chromium ranges in this alloy varies from 20 to 30%. So which are the characteristics of the cobalt based superalloys? Let me write it. Okay. So they have quite good corrosion resistance. They have good corrosion resistance. They behave well under creep. So they are good creep resistance and they are easily weldable. Good creep resistance and are easily weldable. If you notice, we don't have titanium and other reactive element. This means that this type of alloy can be easily produced in air. So it makes production and processing of this alloy extremely easier with respect to production and heat treatment of nickel-based superalloys. Cobalt-based superalloys have really high hardness. So they have really high hardness. So that is also retained at high temperature. So this high hardness can be retained at high temperature. So they don't deform plastically even they are at high temperature. So this means that this kind of alloy is good in the application which requires good wear resistance even at high temperature. So this type of superalloys provide good wear resistance at high temperature. But this kind of alloy also has some drawbacks, like they suffer a lot from thermal fatigue because they have high hardness and they are quite brittle. So they are least susceptible to the variation in temperature. So due to this reason, it is not extensively used in gas turbine. So we can use cobalt superalloy as coating. We can use cobalt based superalloy as a coating. Um, this kind of alloy has high hardness and don't deform plastically as we discussed. So we can think to apply this kind of alloy as a coating as a coating of blade turbine, which is used in steam power plant. That is in that is in low pressure and low temperature condition to protect the leading edge of the blade from erosion. So in the first case study, of this lecture, we can go for studying the laser cladding process, which was used to coat the leading edge of the turbine to protect the metastatic stainless steel blade from erosion. So first question is why we have erosion in low pressure and low temperature turbine. So why we have corrosion? Why we have corrosion? Why we have corrosion in low pressure and low temperature turbine? This kind of alloy has high hardness and okay, so basically we know that one. So we have seen that when we are in this kind of part of turbine, the steam has low temperatures and we can have some water droplet that are impinging on the surface of stainless steel. So basically let's see if we have this is our surface, suppose, and we have water which is going to impinge our surface. So this is the water droplets that are impinging on the surface of the stainless steel, and we can have some erosion phenomena on the leading edge of our blade. Okay. So the idea here is to use laser cladding to protect the blade, and so let me draw this setup of the laser cladding process. So laser cladding process looks something like this. Okay. Let me draw properly. This side is H1, and basically from here to here, this side is S2. So H1 is the clad height, and H2 is the clad depth. And our laser cladding setups look something like this. So basically this is the place where we are going to feed the powder. So here is the inlet for the powder particles, and this will be our substrate. Let me do substrate first. Or we can say this is our workpiece. We can say this is our melt pool. Yeah, we are also feeding laser beam. So laser beam we can represent something like this. This is our laser beam. Okay. So this is our melt pool. We call this as a clad layer. And this is our this thing is our bonding zone, and this is our heat affected zone. Okay, and the direction of laser is in this direction. So in laser cladding we have powder flow, which is sprayed at the surface of a component through nozzles, which is melted by laser beam. So we have localized melting of the powder. So we have localized melting of the powder. On the surface of our component. So this means that once powders reach the surface and it is melted and rapidly cooled down to the room temperature. So let's see a case study where we take a turbine blade made by 410 stainless steel. And we apply laser cladding at optimized parameters. So for both the high energy and low energy process, so basically we have two types of process which we are going to focus. So two processes are high energy and low energy process. High energy and low energy process. So the interface of, so for both the high energy and the low energy process, the interface is very smooth. So we don't see much more cracks or pores. But we notice that the shape of the track and track height changes according to the process. So basically, shape of the track and track height changes and the track height changes with respect to the process, whether it's low energy process or high energy process. So with the low energy track, we have more homogeneous coating dimension. Or let me draw the diagram first for both the high energy and low energy process. So suppose I'm taking this. This is my workpiece. So this is my workpiece here. And we had deposited some type of like our coating here, cobalt based coating. Let me do this. Okay. Okay. So this is my coated part. This is for low energy, low specific energy process. Let me draw for high energy process. So again, we are going to repeat again. So this is our workpiece. This is our workpiece. And we have coated it with our cobalt coating, but at high specific energy. So this coating is obtained for high specific energy. High specific energy. So let's discuss the points which you are going to observe here. So we can observe with the low energy track, we have more homogeneous coating dimension. We have more homogeneous coating dimension. So basically we can say that the thickness of the coating is more homogeneous, but in high energy coating the shape is changing because the thickness is higher. Thickness is higher. And it occurs because when we are applying high energy to melt the powder, we are melting this powder in more efficient way, and so we are providing more material to the track. So we can say we obtain non-homogeneous thickness for the coating here. So other question is like what happens at the interface area. So what happens at the interface area? I mean this interface area here. Basically what is going to happen? We will see that the microstructure of the superalloy is dendritic. So microstructure for superalloy. Microstructure of our superalloy is dendritic. Is dendritic. And we have bright area which is a single phase, so that presents the exactly the interface position between sphere light cobalt superalloy and our martensitic steel. The composition of the bright layer is same for both in low and high specific energy cladding, and the composition of the thin layer is same as the composition of the powder material of the copper superalloy, but it is enriched in iron. So this means that we have interface between the substrate and the coating layer, and so we have an enrichment of iron on that area. So we have an enrichment. We have an enrichment of iron on that area. So underneath the interface, we have heat effective zone. So we are providing an energy through a laser on the surface of our component. So this means that the heat will dissipate through our component and we will perform some sort of heat treatment on a small fraction of our material. So we are changing the microstructure feature in that portion to obtain different property. So what we can do to further characterize this component? So we can perform some hardness measurement to understand what is going on between the martensitic steel and the cobalt superalloy. So we obtain some plots which I'm going to draw, and let's discuss on the results of that plot, and further we can wind up this lecture. So this is the last part I'm going to teach you right now. So we obtain two plots for two processes, that is high specific energy and low specific energy. Okay, so let's start by drawing the plots. So on the x-axis we have basically distance from the interface, distance from the interface, in millimeter. Also here distance from the interface in millimeter. On y-axis we have hardness, or we can write hardness as this thing, hardness, that is bigger hardness. Okay, or let me divide into some plots like this thing. I don't know how much perfect would be, but I will try. Okay, so it is, here is -1, 0, 1, 2, 3, 4. Same for here. Here is -1, 0, 1, 2, 3, 4. And here will be 100. Here will be 200. Same for here and here. Okay. Here will be 300. Okay, here will be 400. Here will be 500. Okay, and he'll be just approximately 700 here, but I'm not going to draw, no need right now. Okay, and let me choose other color for here. I'll use this. Okay. Oh yeah, sorry, I forgot to write here. 100, 200, 300, 400, 500. Okay, now it looks good. Okay, so let's talk about the results. Basically, this is for first graph is for, I'm confused regarding color selection. Sorry. Okay, so this is for high specific energy, and this is for low specific energy. Now let's brag about it, or let's talk about it. So we are looking at the cross section of our tracks. We are selecting at the interface as 0. So this is our interface. Interface here, and this is our interface here. And we are looking at the hardness of our cobalt superalloy and the substrate. So we notice that for both samples, we have hardness value of 500 Vickers hardness. And when we reach the point of the interface, we have increase in the hardness. So we have increase in the hardness when we reach the interface. Because we are also applying cladding of iron to the composition of our superalloy. So we have mixing of the elements which provides increasing of hardness. So in high specific energy, so basically in this plot, we end up with 250 Vickers hardness, which stays approximately 2 millimeter. So which stays consistent till 2 millimeter. So this area corresponds to the heat affected zone area. So still we have mix of some elements, as the hardness is greater from martensitic stainless steel that we are looking at. So the hardness of martensitic stainless steel is around 170 HB. Now let's talk about the low specific energy. So the hardness value of heat affected zone is slightly higher, closer to 300 Vickers hardness, which is higher than the high specific energy thing. But the extension of the heat affected zone is small. That is, I think it's approximately 1 millimeter, and this was 2 millimeter for high specific energy. So this condition is not ideal. So we can say low peak energy is not ideal. It's not ideal. This process is not ideal. One if one to apply the component, because we don't. So we have heat affected zone only for 1 millimeter, but this one is yielding but this one is resulting as for higher, like 2 millimeter. So we can think to apply successive heat treatment like annealing to stabilize the hardness values inside our component. Now I think let's stop, and in the next lecture we can discuss about the nickel based superalloys. So for now, thank you.